Hello and welcome to another LeetCode video. Today we're going to be working on check if there's a valid partition for the array. And so in this problem, you're given a zero index array nums, and you have to partition the array into one or more contiguous subarrays. And we have three conditions that we can follow. So essentially we have to break down this array into subarrays that follow one of these three conditions. So the first condition is you have an array of two numbers that are the same, and you have three numbers that are the same, and then you have three consecutive numbers. And if we can break down this array into an array of, into chunks that are all of these, then we should return true. So let's look at the first one. So we have 4, 4, 4, 5, 6. And we can break this one down because 4, 4, 4 is this one over here. And 5, 6 is this one over here. Actually, sorry, wrong way. So we want to break it down like this. We want to break it down to 4, 4, which is 2. And then we want to have 4, 5, 6, which is a continuous sequence. So that's that one right there. Okay, and that's how we would break that down. So this would be valid. Now let's look at the second example. So here we have 1, 1, 1, 2. So the only way to include the 2 is you need to break it down into this, right? So you would have to break it down like this, but you can't do this because you need three numbers in a row. So there's no way you can include the 2. So you could break down into like this, but essentially there's nothing you can do to include the 2. And so for this, we want to return false, while for this one, we want to return true. And if you're looking at this problem and you're thinking, wow, this is a lot like the previous problems of the day for the last few days, well, you're definitely right about that one. So you might think like maybe there's some kind of sliding window or some kind of backtracking or something, but like we have to have an efficient algorithm. So our constraint is something like 10 to the 5th. So we actually need an n or n log n complexity. And it's not really easy to make a sliding window because essentially at every single point you have to make choices. Like here, you're like, okay, do I want to take two numbers? Or actually here, do you want to be like, do I want to take two numbers or three numbers or what? And then after you make that choice, then you're like somewhere over here. And so there's a lot of backtracking and like, it wouldn't be great. So instead of a sliding window, we're going to focus on another solution. And we're going to think, okay, well, what do we need to know? And what choices can we make? Well, at every index, what three things are valid? Well, it's one of these three things, right? We either have to break our array up into this, into 2 in a row, 3 in a row, or 3 increasing numbers. So this one right here. And so we can just simply go to an index and just try all three, right? That's still linear time because we only have 3 operations. So let's think about what state we would need to save for that kind of problem. Well, all we would need is just our current index. And then at every index, we can just check for these things. We can just check like, okay, can we do 2 in a row? Can we do 3 in a row? Can we do, like this one? And we can just check all of these. And if one of them works, then we can return true. So let's think about our state. So our state is actually our index. And so this is going to be a DP problem. So this is going to be a DP problem. And so for DP, you need states. This is going to be the first thing. State is just going to be the index here. Going to keep it simple. Now, what are the base cases? So base cases. Let's think about those. So what can happen? So we are going to be checking for like 2 in a row, 3 in a row. So we are going to check in our actual DP if we have enough numbers. So we can't really go out of bounds, but we can run out of numbers to check. So if our index equals length nums, then we've checked every single number. And so what do we want to do there? Like if we got here and we're essentially said we chunked up our array here and we got to the last number. So here we want to return true because we successfully did that. Now it turns out there is no other base case because we're going to be checking 4, 2, and 3 and stuff numbers in a row. So we're never going to go like too far out of bounds, right? We're never going to be like over here and then be like, let's just go over here or something. No. We're going to either go 2 numbers ahead, 3 numbers ahead. Yeah, either 2 or 3 numbers ahead, and we're always going to make sure there are actual numbers, right? We're going to like, in order to see 3 in a row, we're actually going to check like, does this 3 in a row exist? We're not just going to like try to go over here somehow. So the only index you can go to is the index right after the one you were at, essentially. That's the only one you can go to. Now we do have caching. Obviously, we're going to want to have caching because you can get to the same place multiple times. And an easy way to see that would be like, let's just say we have a bunch of 3s. So the infinite threes. So here we can go up 2, and then we can go up. So let's say we have another 3 here. We can go up 2, and then we can go up 2, or we could also go up 3, and then go up 3, and we'd be at the same index the same way. So there's a bunch of ways you can get to the same index, but to make a long story short, you can't get to the same index, so we're going to want caching. Now for caching, this is going to be a little different than other problems. So for caching, normally we have a visited set, but if you think about it, for this problem, if we ever hit a true, what does that mean? So if we hit a true, that means we reached the end and we've successfully parsed. So that means there is a valid solution. So if we ever hit a true, that means that we have a solution. So we don't need to like be caching anything. We can just say like, let's just recurse all the way up and we're done, right? So for our caching, normally we use a hash map, but here we're actually going to use a set, and our set is going to include indices that we visited, and every single one of those is going to be false, because if we ever hit something true, we're just done right away. We don't have to count like how many valid partitions are there. We just need to find one. And so in that case, we can just use a set that's going to include all the indices that we failed at, and then once we find one successful index, we're done with the problem. Okay, so now we have our base cases. Right, so this set, so our base case is if our index is in the set, we can write that. So if index in set, we failed. Because the only indices we're going to store are indices that we failed, because if we ever find a successful index, we're done with the problem. Okay, so the last part of the DP is the recursive cases. And so for that, what recursive cases do we have? Like, what things can we do? What are the steps we're allowed to take? Well, they're actually just literally drawn out right here, right? So we have to check for 2 numbers in a row. So we check for 2 numbers in a row. And so let's say we're at index I. Where would we want to go if there are 2 numbers in a row? Well, let's take a look, right? So let's say we are at this index, and there are 2 numbers in a row. So we'd actually want to go 2 numbers ahead, right? We want to go to this index over here. Because if there's 2 numbers in a row, we don't want to go to the next one. We want to go to the one 2 ahead. Because if there's 2 numbers in a row, we're going to say, okay, we're just going to take these 2 numbers. This is going to be our path. This is going to be our chunk. Now let's just check 2 numbers ahead. So for 2 numbers in a row, we have to check dp plus 2, right? Or index plus 2 as the index, so dpi plus 2. And if that's true, then we're done. Like any one of these recursive cases, if that's true, we're done. Let's actually write that one more time. So we have to check dpi plus 2, index plus 2. Okay. Now let's actually write over here. Okay. So now we have to check for 3 numbers in a row. And where would we have to go for that? So we'd have to go dpi plus 3 now, right? Because we're skipping the current number we're at and 2 more numbers. So like if we're over here and we want to check 3 numbers in a row, now where we would jump, well, we would be jumping to this number here. So that's 3 numbers ahead of our current index. Okay, that's the second case, fine. Now what's the third case? Check for 3 numbers that are increasing by 1. Right, that's this last case where we have like a 3, 4, 5. And then where would we have to check? We'd have to check dpi plus 3 there as well. And so these are our 3 cases, and if any one of these is true, we can just return true because we've successfully partitioned. And so if all of these fail, so we can write that as well. So if all of these fail, the array from this index couldn't be partitioned, and we need to put the index into the visited set, right? Saying like, okay, we tried from here, nothing worked, and then we need to return. And if any one of these passes, then we can just return true right away because we have successfully partitioned. So that's pretty much it for this problem. For the memoization is you have an index as your state. You have base cases where if we get to the length of the nums, we've successfully partitioned. Then we also have a caching set, and if the index is in the set, we failed. And then we have these 3 recursive cases over here. Okay, so let's actually take a look at the code for this problem. And so let's actually go up here. So this is going to be the code for the memoization solution. And let's actually do this so we can see it, and we'll go over it briefly. So essentially, it's what I said. So this is our case where we succeeded. This is if our I is in our set, we failed. And now these are our checks. So first of all, if we have to check 2 numbers ahead, we actually have to make sure like we're not out of bounds, because this nums is only, you know, linked nums. What you could do to make it easier to get rid of these checks if you wanted to was you could just add a few numbers to nums. So you could add like 3 numbers to nums and just make sure that you save the length nums as like your initial length nums. That way you won't have to do all these out of bounds checks. But essentially, if you're not out of bounds and nums I equals nums I plus 1, that means you have 2 numbers in a row that are the same. So then we are checking over here. And if this is true, then we can return right away. And then we have this subcase. So if 2 numbers are the same, then we know 2 numbers are the same. So now we can just check for the third number being the same as part of this same if statement, right? So if this is true, then we can just check for a third number. So we'll just say, okay, if the third number is in bounds and the third number equals the second number, we're going to check over here. And now finally, for the last case, we're going to see, okay, and also if we're not out of bounds and we have 3 numbers that are strictly increasing, so that's the case of like this kind of situation, then, okay, perfect. Let's just go 3 numbers ahead. If that's true, then let's return true. Finally, if all of these fail, let's just add it to the visited set and return false because we failed. And then finally, we need to return memoization from the first or the 0 index. Okay, cool. So now let's go to the next part of this. So we're actually going to delete some of this. And we are going to redraw this problem. So let's actually delete this as well. Now this should work. There we go. Okay. And let's actually redraw this. And now let's figure out a bottom-up solution as well for this problem. And we're going to focus on this one right here, this 4, 4, 4, 5, 6. So what we're going to actually do is we're going to make an array. You could do this a few ways, but we're going to, I honestly don't remember what I did for my problem, but it wouldn't really matter. So essentially what we're going to do is we're going to make an array of length nums plus 1, and I'll show you why. So this is going to be length 6. So 4, 5, 6. And we're going to have indices here, so this is going to be index 0, 1, 2, 3, 4, 5. Okay? And now we are going to put in some numbers here. So essentially what we're going to do is we're going to initialize everything to false. Initialize everything to false, except for this last number. So this is our base case, right? Like this is when index equals length nums, right? That's our base case. So this is going to be this, because length nums here is 5. So if this is true, we're going to do that. Okay. Now, essentially, all we have to do is we have to iterate backwards through these things, and we have to check for this 1, 2, 3. So we are going to write down this 1, 2, 3, and we are going to just draw our nums array somewhere here just to check these things. So our nums array is going to be 4, 4, 4, 5, 6. And we are also going to draw the indices just to like show us, to make it easier for us later. So this is index 0, 1, 2, 3, 4. Okay, so starting at here, we have to check for these 3 cases. So 2 in a row, 3 in a row, and 3 increasing by 1. Call it 3 increasing. Okay, so let's start doing that. So for this 4, that is going to correspond to this number here, right? So do we have 2 in a row? Obviously not, because we're at the last number. Do we have 3 in a row? Obviously not, because we're at the last number. And are there 3 increasing? Obviously not. So there's none of those. So none of those are true. Okay, well, if none of those are true, that means this is going to stay false. And then we are going to go to the next one. So now we are going to go over here, and that corresponds to this 5. Okay, well, for this 5, is it 2 in a row? No, they're different. Is it 3 in a row? No, because that would be out of bounds. And is it 3 increasing? No, because that would be out of bounds. So none of those. So this stays false. Okay, now we're at this 2. Yeah. So we're at this 2, which is this thing here. Okay, is it 2 in a row? No, they're different. Is it 3 in a row? No, they're different. Is it 3 increasing? Yes. And so because it's 3 increasing, what's the index we have to look at? So we actually have to look at index 5 here, which is true. Or sorry, it's not going to be this nums, but essentially the index we have to look at is 3 numbers ahead, right? Because it's 3 in a row, so we have to look 3 numbers ahead. So we're going to look all the way over here and we're going to say, what's that value? Oh, that's true. Okay, so then in that case, we're going to replace this with true. So whenever one of these is true, we have to OR our value with whatever's over here. So we can write that down. If one of these is true, we need to OR our value with corresponding value at index. And so for 2 in a row, we would go up 2 indices. Then for 3 in a row, we would go up 3 indices. And then for 3 increasing, we would also go up 3 indices. Okay. So now that for this one, now that that's true, and we did find something, okay, that's good. Now let's actually go to the next number, right? Like this did work. And so yeah, so if one of these is true, and whatever index we went to is also true, that means that number has to be true, right? Because we are ORing it with whatever is at that index. So only one of these has to be true, and the value of the corresponding index has to be true. Okay, so now we are over here. And that's going to be corresponding to this. So are there 2 in a row? Yes. Okay, well, for 2 in a row, we would go up 2 indices, right? So for 2 in a row, we would actually check over here, and that's false. So false or false is still false. So that doesn't really do anything. Are there 3 in a row? No, there's not. Are there 3 increasing? No, there's not. So this stays false. Now we finally go to this first one, which is corresponding to this. Are there 2 in a row? Yes. So 2 in a row would be, you go up 2 indices, right? You want to go to this value. So let's check over here. This is true. That means if that's true, we're going to OR our false with the true, which would give us a true. So that would be true. Are there 3 in a row? Yes. And that would be over here. So we're going to OR that with a false. True or false is true. And then finally, are there 3 increasing? No. Okay. And then finally, we return this value here, which would give us true. And you can do the same thing for this. That would be totally fine. And so there is one other thing that I wanted to mention, and that is we could do a slight optimization here, right? As you notice, we are only going up 2 or 3 indices. So like the most we'd ever go for checking this value is over here. And so what we can actually do is we can just only store the last 3 indices, right? So we can just store the last 3 indices, and then instead of having O of n space, we would have O1 space because we would have the last 3 indices. So let's show that for the last part here. Okay. So what we're going to do is we are going to delete some of this, and we are going to just show the last 3 indices. So essentially what you want to do here is you want to make an array of length 3. And what you want to do is you want to make your values true, false, false. Because these are the values that represent index like 5, 6, and 7. And so at index 5, that's our base case, but at index 6 and 7, it's false. Right? Like these are out of bounds. You can technically never really get here, but you just want some default values. And so now what we're actually going to do is I'm going to show you. So now we're going to kind of do the same thing. We're going to start at, so this is going to represent the values at, let's just write that as well. So this is going to represent the values at, even though this is 0, 1, 2, this is going to represent the values at index 5, 6, and 7 for now. And now we are going to start at this value here. So we're going to start at the last value in nums, essentially, and we're going to do these 3 things. And for this, we're just going to have a temp value. So we'll just have some temp value. You could do this a few different ways. Or also what you could do is you can make an array of 4 elements, right? Either one would work. And then you could do that as well. I forgot which one I did in my solution, but you could either do 3 in a temp value, or you could do 4 where this starts as false. Let's maybe do that. Let's just have 4 values where this first one starts as false. So this would be a little bit easier now. Okay, so this is like what our starting array is, and now our solution will always have only 4 values. And let's just go through that and show what would happen here. Okay, so we're going to check. We're going to start at this value here, right? Because this is our base case, and we don't need to check these. They're just here because they're kind of like fillers. Okay. So are there 2 in a row starting here? Obviously not. Are there 3 in a row? Obviously not. And are there 3 increasing? Obviously not. Okay, that means this stays false. But now we have to figure out, like, well, okay, so if this stays false, what are we actually doing here, right? And so essentially what we need to do is we need to pop the last value. So we're going to pop this value. And then we are going to, but instead of actually popping and pushing, like you could pop and push if you wanted to. Honestly, the space complexity, because you only have 4 values, let's just say you pop and push, right? It would be the same thing. So we're going to actually pop this last value, and we're just going to push a new value at the start. So now this is going to be F, and now this is going to be corresponding to index 3 now in numbers. So that's what we're doing at every step. We're just popping the last value and then pushing at the start. Okay. And so now we are going to be at this value here. And so for this value, are there 2 in a row? No. Are there 3 in a row? No. And then are there 3 increasing? No. So this stays like this. Then we pop. Let's actually maybe copy this somewhere just so we can like, whoops. Let's actually, we don't need this anymore. So let's actually just get rid of that for now. Yeah, I don't think we need it because essentially we already have our array here. So let's just get rid of that to give us more space. Okay. So let's actually do the next value now, right? So we pop, now we need to push. So we are going to push, and then remember our default push value is just going to be a false. Okay, and this is going to represent index 2. And so you see, like, we only have 4 values at every time. We're just popping and pushing. And I'll show you what you could do instead of popping and pushing, but it ends up being the same time complexity essentially, so popping and pushing is fine as well. Okay, so now we are at this 2. So we need to check, are there 2 in a row? Well, no, right? Are there 3 in a row? No. And are there 3 increasing? Yes. So if there's 3 increasing, we need to go up 3 values. And so that's what we're going to do. We're going to go up 3 values. And you can see this is true. So now we're going to, remember, we're ORing these. So now we're going to make this true. Okay. Now we are going to, once again, we're going to pop and push a new one at the start. Initialize to false. Okay. And so that's that. And that's going to correspond to this value over here. Let's draw it in blue like the rest of them, right? Okay. So now we need to check, are there 2 in a row? Yes. Okay, so for 2 in a row, we are going to OR it with this value. Well, that's false, so there's nothing there. Okay, are there 3 in a row? No. 4, 4, 5 is not 3 in a row. Are there 3 increasing? No. Okay, so we're done there. Now we need to pop again. Push. Remember, default value false. Okay. Now we're at this value. We'll just leave this as green. This is our last one. Are there 2 in a row? Yes. And the index would be 2 up, right? So it would be this index over here. And so this is going to get replaced with a true now. So we do have true. Are there 3 in a row? Yes. If there's 3 in a row, you'd want to go up 3 indices, so that would be over here. And so true or false is true. Technically, you could literally just say, like, once you get one of these to be true, you can just skip the rest if you wanted to. Maybe that would save you some time, you know? So you can just say, like, okay, if this is true and the value is true, let's just skip the rest. So that could be like a slight optimization. It's going to be the same O of n anyway, but yeah. And are there 3 increasing? No. And so now we would want to return this value here, and you can see our array is only 4 numbers. So I think this is something like 10 to the 5th for the array length, and so without the optimization, we would have 10 to the 5th numbers, or, you know, booleans. But because we are doing it in place, because we recognized we only need to look 3 ahead, so we just store 4 numbers. And so this is super common. Well, maybe it's not super common, but this is something you're going to want to look out for. So let's write this down. So for bottom up DP, look how far ahead your, or I guess how far ahead your current state needs to look to get its answer. If all of your states need to go up a constant amount, like 5 or 10, we just need to store that constant amount of states and can do the work in place. And so like for my last 2 or 3 problems, pretty much all of them have done this kind of thing where you have top down, bottom up, and then space optimized bottom up. And it's all the same pattern where you just recognize you only need 3 or 4 states, right? Like for house robber, you only need 2 states. I haven't done house robber here, but in house robber, you only need to look 2 states ahead, so we're saving 2 states. Here, we only need to look 3 states ahead, so we could save 3 or 4 states. It doesn't really matter, same space. It's just constant space. And so there are some difficult problems. I think I did some like stone game problem where you're only looking 10 ahead, but for that one, it was actually like a really hard problem, and you needed to actually, not only did you need to get the bottom-up DP, you also needed to do the space-optimized bottom-up DP because those states were really tight to fit in there. So you actually needed to do the space optimization. But you can see like it's all the same thing, right? It's literally all the same pattern. We need to use only a couple of states. But if your states needed to like loop through all of them, then you could never do the space optimization. So just look when you're getting your states, see how far ahead your states need to go to get their output, and that will give you a huge hint in if you could do a space optimization or not. In this case, we could. So let's take a look at the code. Okay, so this is our memoization. Now here is our bottom up. And so you can see it's pretty straightforward. We just initialize everything to false. We make our last state equals true. And then essentially, this is basically a copy paste of these conditions, right? So we're just checking, you know, is this state actually in bounds? And do we have 2 in a row? If we do, let's OR those together, as I said. And then do we have 3 in a row? If we do, let's OR those together. And then is our last one in bounds? And do we have 3 increasing? If we do, let's OR those together. And like I said, you could make an optimization where if one of these is true, like let's say this OR is true, you can skip the rest if you wanted to. It's not going to save anything really. And so this bottom up does work. Okay, this bottom up does work now. And we can take a look at the, so you can see it's reasonably efficient. Let's comment it out. And let's take a look at the space optimized bottom up. And so what you're going to notice is the space optimized bottom up is pretty much the same code as this, almost the same, except now we only have 4 states. We are still looping. The loop is the exact same loop, but now what we're doing, so instead of doing a push and a pop, I just manually change these values. So if you think about it, if you have values like 1, 2, 3, 4, and you are adding some value like 0 and you're removing the 4, then essentially all your states are the previous values. That's what I did here. So like DP1 would be DP0, DP2 would be DP1, but essentially a push and a pop would give you the same thing. In fact, we can even do that if you wanted to. So you can do something like, so essentially what we would do is we would do a pop first, I believe, right? Yeah, I think so. Okay, so let's just give that a good try. So we could say like dp.pop, and then we could say dp.insert. Hopefully this works. Let's take a look. So this should theoretically work. Okay. I was getting a lot of like errors when I was doing these earlier, but yeah. So you can see it's pretty efficient. It's a lot more space efficient than this top one. But like I said, that depends on test cases really. Either one is the same thing. And the reason you could do a push and a pop and, you know, like pushing into the front is generally bad, but because this is only 4 elements, it's just constant time anyway, inserting into the front. And so, but you can see the rest of the code is pretty much all the same. And so the only difference is now we are doing this. So once you do have your bottom up, it's really easy to change the code. All you do is you just change this into a smaller DP, and then the loop constraints end up being the same, but you just have to figure out like, okay, I don't have DPI anymore. What does DPI need to be? And everything else is almost the same. But yeah, I think let's also write the time and space complexity. I guess we forgot to do that. So for the time, it is O of n because we have n states in every single one of these, right? So let's just uncomment this again. Let's comment where we have our stuff. So for the memoization, as you can see, you have index states, and you're doing 3 operations at every single one, which is constant time. So this would be O of n time and O of n space because you have n states. For the bottom up, same thing. You have an n length DP, and you're doing 3 operations every single time. So that's O of n and O of n. And finally, for the space optimized bottom up, we have O of n time as well, but now we have O of 1 space because our DP is only 4 elements maximum. You could do 3, you could do 4, but either way that would be O1 because it's constant. But yeah, that's going to be it for this problem. So let's write space here. And if you did like this problem, hopefully you did, please like the video and subscribe to the channel. It really helps grow it a lot. And yeah, I'll see you in the next one. So thanks for watching. And if you go want to, by the way, I am releasing TypeScript videos on the Blind 75 for LeetCode. I should be releasing a few every day. So if you want to learn TypeScript and practice the Blind 75, I'd encourage you to check out that playlist that I'll be updating. But yeah, I'll see you in the next one. Thanks for watching.